little bit of info. As Lauren introduced me, I am an assistant professor at the School of Computing at Wichita State University. We are located right in the middle of the US, right here in Wichita, Kansas. At WSU, I lead the Cyber Physical Systems Security Research Lab. Currently, 3 PhD students and 2 undergraduate students working with me in the various topics of security and resiliency of cyber physical systems. I'm sorry, my slides are not moving for some reason. Okay. In the past, I got my PhD from University of Illinois Urbana-Champaign not too long ago. I graduated last December. And before that, I spent 3 wonderful years at University of Manitoba in Canada, where I did my master's degree. So my current research interests are in the intersections of system security and networking, in particular exploring the various security and resiliency aspects of cyber physical systems. So in recent days, my students and I are working in various topics of security in real-time and distributed IoT-style edge computing systems, especially looking more on the operating system side, security on real-time operating systems, use of more hardware software-based techniques such as trusted computing modules and trusted execution environment, especially use those security extensions for real-time aware systems. On a different direction, I'm sorry, for some reason my slides are not advancing. On a different direction, I also looking on using novel networking technologies such as software-defined network to provide more resiliency and safety guarantees in cyber physical networks. In the past, I spent some time on exploring security and resource management techniques in cellular wireless networks such as LTE and 5G networks. And in recent days, I started exploring security and resource management techniques for vehicular communication networks, especially use of vehicular communication networks over the cellular radio channels. So enough about the introduction. So let me jump into the today's talk. I'm sorry. Okay, so let me jump into the today's talk. So today I'll be talking about our recent work on security for cyber physical systems. So before jumping to the details, let me give a little bit of background so that we all are in the same page, and then I'll drive more details into the work that I'm going to present today. Okay, so what is a cyber physical system? So as the name suggests, so it coupled with the 2 parts, cyber and physical components. So in the cyber physical system, the cyber components are all the software control algorithms, program logics, and the network and communication stacks, and also the actual hardware platform where those logics are implemented, such as the microcontroller, electronic control unit, programmable logic containers, and whatnot. So those cyber components are coupled with the physical components, such as the sensors, actuators, and actual plant, make those whole cyber physical platforms functional. And these cyber physical systems find use in many applications, such as the more traditional use cases, such as automobiles, avionics, industrial control systems, as well as many emerging and newer technologies such as remote surveillance, drones, autonomous driving, smart manufacturing, robot-aided healthcare are just a few examples to mention about. as we can see from the applications, those cyber physical systems work in a very diverse domain, and often they are very safety critical in nature. So the question is, uh, what about those security aspect of these safety critical cyber physical systems? So in early days of the design of cyber physical systems, designers are not explicitly concerned or care about the security in the design of cyber physical systems. So this is because in traditional cyber physical systems, they use more custom hardware. So they use proprietary operating system and software, and they are kind of like they don't have enough network connectivity, so they are kind of remain an air gapped isolated system, remain isolated from the other competing entities. But in modern cyber physical system, as you will probably see from the newer use cases, so they are now use the developer now use more off-the-shelf hardware. They tend to use more open source software and OS due to the increasing complexity of those modern systems. And more importantly, they are now have many connectivity options, and they are often connected to the unreliable medium such as the internet, especially with the emergence of newer Internet of Things specific applications. The modern cyber physical system are more connected than they were in the past, which means there are now larger attack surface, and which makes them modern cyber physical systems are vulnerable to security threats. And in fact, there has been quite a few real world attacks that shows that threats to the safety critical cyber physical systems are real. For instance, the now famous Stuxnet worm that caused a serious damage to an industrial control plant. Also, there has been some real world attacks on automobiles, police drones, and other manufacturing plants. So all of those real world attacks shows us that threats to the safety critical cyber physical systems are real, and we need concentrated effort to make those critical systems secure. So given the increasing cyber risk, so the goal of our research is to come up with a technique that allow us to provide security guarantees in a cyber physical platform. So one of the critical challenge in CPS security is that unlike traditional general purpose computer systems, so security issues in a cyber physical system can also lead to safety violations. So one example I can explain, I can like consider like a autonomous vehicle or any automobiles where and the airbag deployment of an automobile, for instance. For instance, when the front bumper sensors some collision, then that it needs to be notified to the actuators and on airbag deployment platforms, and then the actual airbag will be deployed to ensure that the passengers, driver and passengers remain safe during the collisions. Now, if there are any attacks or any safety violations in between this sensing of the impact and from the airbag deployment, and the airbag couldn't be deployed due to software bugs or intentional attacks, then it will threaten the safety of the passengers and drivers. So the point I would like to highlight that the security violations could have serious safety implications due to the safety critical nature of the cyber physical systems. And another key point I would like to highlight that it's really difficult to ensure a full secure proof system. I mean, full secure system. So no matter how much security monitoring or intrusion detection techniques we can introduce or integrate in the system, we cannot guarantee that 100% time it will be work perfectly. So there could be some backdoors, some zero-day vulnerabilities that could make the system vulnerable to the attacks. So to considering those two facts, so in this work, we want to develop a technique that ensures the physical safety of the system despite being considering the fact that it could get compromised. And instead of doing kind of trying to find out like intrusion detection and monitoring technique, we want to make a solution that ensures that no matter what actions an adversary could take, the physical safety of the system remain functional. For instance, if I go back to the airbag deployment example, so even though the attacker could make some changes in the airbag deployment module, our ultimate goal is to ensure that during the impact, the airbag should be deployed. So kind of those safety goals should be remain satisfied. So how do we do that? So to do that, our proposed idea is to develop a technique that prevents the attacks from being progressing. So no matter the way adversary could take or get into, intrude into the system, make some damages. So the key goal here is to come up with a technique that prevents the attackers from making much more damage into the system. So how we do that? So we came up with an approach that allows to reboot the system based on certain conditions and load a fresh copy of the image so that we ensure that always we have a uncompromised copy of the system available at the runtime. And in the latter part of the talk, I'll show some of the issues with the first approach that allows the system reboot, and present another approach that provides the same functionality but use a modern modern security architectures provided in the newer processor that's called ARM TrustZone technology. So I'll talk about how we can leverage these newer processor extensions to provide attack resilient server physical platform. So we refer to this as a proactive mechanisms because instead of actively checking for intrusions and based on intrusion, taking some response technique, we will proactively do some cleanup, for instance, the rebooting the system that prevents the attacker from making any meaningful progress in case of there is any intrusion. So I'll talk more about this approach in later slide, but just giving you some heads up. All right, so in the rest of my today's talk, I will go over this approach. So we call our framework ReSecure. We presented this work in ICCPS back in 2018, and we also have one follow-up work that we published in the IoT journal. So I'll talk both of this paper in a very high level in next few slides. Okay, so like I said, so our idea is to reboot the system based on certain conditions and ensure that always we have an uncompromised copy of the operating system and application images during runtime. But this is not an easy task, especially given that the use cases of cyber physical platforms. For instance, we cannot simply reboot a operating system or applications for a drone, for instance, because it may the drone applications could be unavailable at certain point and the drone may crash during the mission because of lack of signals going through its different peripherals. So we need some sophisticated technique to ensure that this reboot process works properly. So how do we do that? So we use a special controller called safety controller, and we use a hardware root of trust module that allows the reboot process function. So I'll talk more about this thing in just in a second. So like I said, so we use a different set of controller, and we have a hardware root of trust that allows the reboot. So how the ReSecure framework looks like. So we have a host platform where we execute our operating system, and we have a read-only storage area where we store the uncompromised fresh copy of the operating system and applications that given by the designers. And the platform runs two special controllers. So the controllers are, you can think of the applications space, like the kind of like the actual applications that drive those cyber physical platforms. So we have two different type of controller. One is untrusted controller, where we can potentially run all our control applications and all the required applications required for operating the platform. And we also have a safety controller that is like a very small minimal pieces of code that is verified by the designer, and it is kind of remain isolated from the untrusted controller and ensures that all the programs running in the safety controller remains uncompromised. And we also have a separate root of trust module that interacts with the safety controller through some IO interface. In our current implementation, we use the I2C handler, and that uses some timer module to ensure that we can have this restart functionalities, and those restart feature cannot be tampered with. So let me go over the workflow of the ReSecure framework. So our goal is to ensure that even though there is any intrusion, so we will ensure that the physical safety of the system will be preserved. So the key idea here is that for a given state of the cyber physical plant, we want to find the minimum amount of time that it takes for an adversary to drive to the system to an unsafe state. Now, if we could come up with a mechanism that reboot the system before that amount of time, then we can ensure that even though the adversary could intrude into the system and compromise the application logic, he or she will not have enough time to crash the system, so to take it to an unsafe state. So let me give an example so it will be more clear. So again, consider a drone. Let's say the trajectory of the drone looks like this. So this is like the X dimension shows the time, and Y axis shows the Y dimension shows the corresponding altitude of the drone. Now, let's say this red horizontal line denotes the unsafe altitude, which means if the drone's height is below that red line, the drone may not be come to a safe height and it may crash to the ground. Now, let's consider a case and a point of time where an adversary compromised the drone's logic, and let's say it make the changes in the code so that the drone's propellers cannot get the desired signal, and it remains it stop rotating. So because of the physical inertia of those cyber physical systems, so the drone may not be crashed to the ground immediately. So it may take some time to take the drone to the ground due to those physical inertia. So that means we have some buffer time after the attacks and the actual safety violation time. Let's say this is the time that takes the drone to an unsafe altitude. So if the drone's altitude is lower than that height, it may not be able to come up to a safe altitude. Now, if we could come up with a technique that make the drone's applications rebooted and load from the uncompromised copy, then we could take out the drone from an unsafe altitude to a safe altitude. Sorry. as shown in the in that blue circle. But the challenge is that, so how do we find the reboot time? So how do you know what's the amount of time it takes us to reboot the system so that we can ensure that its safety conditions are remain intact? So to answer the question, so let me go over some of the background of the cyber physical system state and show me some of the definitions. Then it will be more clear. So let me introduce two terms. The first term is the admissible state. So again, if we go back to the drone example, the admissible states says that the set of state of a cyber physical platform that do not violate its safety condition. For instance, if we again take the drone example, the gray shaded region here shows the altitude of the drone where the drones remain in a safe height during the mission. We also let me also introduce another term called recoverable states. So essentially, these recoverable states is a subset of admissible state, where at any point in time, if the system is in the recoverable state, we can ensure that it will remain in the admissible state. Which means, so if we are in the recoverable state, we can ensure that our safety conditions will be satisfied. So why we need these state definitions? So that will be clearer in the next slide. So let me introduce another term. It's called true recoverable state. So essentially, this is a recoverable state where we can come up to an admissible state within a certain time, a certain amount of time. So here we're in this case, I'm saying we say our state is recoverable, true recoverable, if we can come up with an admissible state, which means we can stabilize the plant within certain alpha time. So let me give an example, then it will be more clear. So let's ignore the maths and just I'm showing the cyber physical state in a two-dimensional plane for the sake of illustration. Let's say these yellow rectangle shows the admissible state, and this green sub-rectangle shows the recoverable state. Now, let's consider we have a given threshold alpha equal to 5. Now let's consider cyber physical state for in this plane as shown in this bullet point. Now from this point, the system could come into a recoverable state within t equal to 2 time unit. Now let's consider another point which is slightly in the edge of the recoverable region. From that state, the system came up to a recoverable state in t equal to 3 time unit. So these both 2 points are true recoverable state, because from those points we can come up to it a safe region, which means the system can stabilize the physical plant. Now let's consider another point, which is an admissible state. So in that point, the system remains stable. But from that point, we cannot reach out to a safe recoverable region within alpha equal to 5 time constant. So that point is not a true recoverable state. So if the system remains into that state, we cannot take the system to a safe region within our alpha constant time. So those definitions give us the base of how often we can reboot the system to ensure that the system remain functional, or like the system remains stable and its safety constraints are satisfied. So how? So let me give an example. Like I said, so these definitions give us the base of to calculating our reboot time. So it will be probably more clear on this state machine diagram. Let's consider for a given state. Those are showing those sub-rectangles showing the different state a system could move from a current state. And this shaded node shows that a state which is not a recoverable state. Now, if we continue this state machine, for a given state machine, we can find out the amount of time it takes for a given state X to all the subsequent state where the system could go to an unadmissible state. So this gray state essentially shows that if the system remain in that gray state of the plan, so it cannot be recovered, it cannot become to a safe, stable state. By the way, so those state and these state machines of a given cyber physical plans, I mean, how to derive those state machines are kind of well studies, especially in the control community. So for a given plant, finding the state machine and corresponding state exploration of a given cyber plant is known to the designer. So we leveraged already known techniques to find out reboot time and provide kind of like a security guarantee. All right, so let's back to the topic. So what we need to do, we need to find out the time it takes to take from a given state. We need to find out the time that it takes to drive the system to an unsafe state. And then we find out we take the minimum of all those time. So in this example, delta equal to 2 is the smallest amount of time that takes the system to an unsafe state from a current state. So our idea is that if we could reboot the system before that delta equal to 2 time unit, then no matter what actions an adversary take, he or she may not have enough resource and time to drive the system to an unsafe state, because this is the smallest amount of time that needs the system to go to an unsafe region. And our ReSecure techniques reboot the system and load a fresh copy of that image before that amount of time. So this way we ensures the safety of the system instead of without doing any kind of like intrusion detection techniques. So how the overall workflow of ReSecure works? So let me go over. Essentially, this is what I just said. So from a given state, we explore all the states and find out the shortest amount of time and reboot the system before that. So how we do that in ReSecure? So we use the notion of secure execution interval, or ACI. So in this ACI interval, so we perform this reboot time calculation logic and access to, remember we have a hardware root of trust that performs all those reboot mechanism. So we allow the access to the that root of trust only during the secure execution interval, so that we ensure that hardware root of trust is remain that the attack surface to the root of trust is very minimal. So how the ReSecure workflow looks like? So essentially, in the first step, we boot up the software, so we load the firmware and make the platform live. And after that, we enter to the ACI interval. So remember, at this time, we will do all these execution time, like state calculation techniques. And access to the hardware root of trust is only possible during this ACI interval. So then ACI, we run this all this computation through the safety controller to calculate the next reboot time. So based on the current state, we will calculate the next reboot time, and then we set up the timer in the root of trust to ensure that we know when to when to trigger the next reboot. And then we close all the interface to the root of trust so that it's kind of again remain air gapped. And the adversary or malicious entity cannot have the access to that root of trust module. And then we jump to the untrusted controller where we actually run all the control logic. And then we repeat the same process after each reboot. So this way we ensure that depending on the current state of the system, we know when to reboot. And also between these two consecutive reboot, if there is any kind of intrusion, it will not affect the safety of the cyber physical plant. Okay, so far nice idea, but nothing is free. So as the reboot, so there is an overhead of reboot, because during reboot, the system will, even for a certain amount of, or even for a smaller amount of time, the system will not be available, and we need to account that unavailability when we calculate our safety calculations. And also, reboot are very platform specific. So for example, in bare metal, small applications, it could be very fast. But depending on the platform and the type of operating system we use, it could be very large as well. For instance, if we have, for instance, a complex operating system like Linux, it may need to load up all the device driver, IO peripherals, and all the libraries and whatnot. And it may lead to a larger reboot time. And another limitation, I would say, it's like this ReSecure idea needs a custom hardware. So we need a custom root of trust to ensure the reboot. And that may not be feasible for, especially for legacy systems that are like already deployed in the field. So to address these two issues in the follow-up work, we came up with an idea that used the software hardware-based security extensions available in modern processor. So essentially, we use the TrustZone technology provided by the ARM processors that allows to do this similar functionality, but without having a custom hardware, and those reduce the overhead of rebooting the whole platform. So how we do that? So I'll briefly talk about these two topics in next few slides. But before that, let me quickly introduce the overview of the TrustZone technology. Okay, so the TrustZone technology in ARM processor provides a secure isolated environment that isolates the secure execution of software and the data. So what happens in TrustZone, that in TrustZone terminology, we have two different execution environment. So one is the untrusted environment. So in TrustZone, it's called normal world, where we can think of it's like our regular operating system environment. Like we have our user space and kernel space separation, and we can run all the regular and potentially untrusted applications. And also, in addition to that, TrustZone also provides a secure trusted enclave that is called secure world in TrustZone terminology, where we can execute our security critical applications or even a trusted operating system as well. So we leverage this, and these two worlds are connected through a secure monitor that is responsible for switching between normal and secure world, and also ensure that the secure world remain isolated from the normal world. And the secure monitor is responsible for all the context switching and ensure those security boundaries are remain intact. So we leverage this existing TrustZone feature available in ARM processor to further enhance our restart-based idea. So the benefit of doing that is that now we don't need a separate root of trust to provide to ensure the reboot mechanism. So we can leverage the security enclaves available in TrustZone technology to provide similar functionality. So I'll not cover the details now, but I'll just go over the very basic idea how we do for this TrustZone-based extension. So we use kind of the similar notion of the original framework, but instead of having a separate root of trust, we now rely on a hypervisor that is supports the TrustZone technology. And on top of that hypervisor, we run two virtual machines. So one virtual machine is the untrusted controller, which is doing the same functionality as before, where we can execute all of our control logic. And also we run our safety controller within a secure virtual machine in the secure world side of the trust. And now remember what our ultimate goal is to do here. So we need to find the amount of time that takes the system to an unsafe state. So what we do the same calculations as we did before, but now instead of rebooting at that time, we take the control logic to the rebooting the whole platform. We take the now logic to the secure VM, which runs the safety controller, and then the safety controller essentially do and reboot the non-secure VM and all the applications running inside the untrusted controllers. So essentially, our safety controller running the secure VM calculates this next reboot time based on this state calculation analysis that I presented before. And instead of rebooting the whole platform, it just reboots the non-secure virtual machine. So rebooting the VM for sure is less costlier than rebooting the whole platform, but we get the similar benefits. And this TrustZone hypervisor is responsible for provide the necessary isolation guarantees so that the attacker cannot tamper with whatever running inside the secure virtual machine. And this is protected by design through the TrustZone technology. Okay, so let me quickly go over our implementation and some of the results before I conclude the talk. So we implemented this on a 3 degree of freedom helicopter. And we used the Xilinx platform for controlling the helicopter, and we used the FreeRTOS as our operating system for the reboot-based implementation, and we used the LTZ visor hypervisor for our TrustZone-based implementation. And in this experiment, our safety goal is to ensure that the copter is above the ground and do not touch to the surface. So I'm just showing one quick example of our quick results, and then I'll move to the concluding slides. So in this case, we are showing an effect of the DOS attacks where the adversary tries to crash the copter by touching it to the table. So this is kind of like showing an extreme case. So in the plot, in the X dimension, I'll show the time, and Y axis is the corresponding output voltage of the motors of the propellers. And in the figure, the green line shows when the safety controller is running, the red line shows when the untrusted controller is running, and white is the time of reboot. And as we can show here, when the complex controller is running, an adversary turn off the motors, so which essentially stops all the rotation, and that could drive the copter to the ground. But after the reboot, when the safety controller kicks in, it takes the system, it takes the motors to safe height, and the control is recovered, and essentially the copter is not crashed. So let me talk about a couple of ongoing work before I conclude my talk. So far we discussed two ideas. One is the platform level reboot that uses a separate root of trust module, and then we have quickly showing an extension that doesn't need a separate hardware, and it rely on the existing processor extensions such as the ARM trust technology. So we're currently working on to do some kind of another level of optimization on what so far we did. So what we're trying to do, in addition to the platform reboot, can we also do some kind of like a micro reboot that is even less costlier than, for instance, reboot a VM per se? So the key idea here is that, let's say we have a bunch of tasks running in the system, and we can do the full system reboot or full VM reboot as we do before. But in addition to that, can you also reboot the application itself? So that we can reboot the whole platform or virtual machine in a longer time frame, but we can reboot the applications more often to ensure that they always have a fresh copy. But there are several challenges. For instance, how often we'll do reboot, which app will pick for reboot, and if the application has some temporal constant, for instance, I need to do some processing before certain time limit, then the rebooting will affect those timing constants. How do we ensure that? So there are many challenges, and we are working on that to solve some of the issues. And another idea is that coupled with this proactive mechanism and do some kind of like a reactive checking. So the key idea here is that in addition to the two untrusted controller as we discussed before, can we also have some kind of like a monitor that works as an intrusion detection system that observes the behavior of the untrusted controller? And based on that checking, if we can see there is some anomalies, we can do reboot. We can trigger the reboot. For instance, we can trigger the application level reboot. Even we can do the system level reboot, or we can do other action. For instance, we can alert the human operator and whatnot. So that takes to my last slide. So ReSecure is one way to secure the system that kind of use a proactive mechanism that prevents the system from going to an unsafe region and restart based on certain condition to ensure that we always have the fresh copy. And this is just another technique to secure the cyber physical system. So due to their different diverse applications and their complexity, we need like a layered defense mechanism to secure the cyber physical system. So we need a security from the very bottom in the actual hardware, in the sensors, actuators. So we need the security solutions at the operating system level, at the application level, at the network itself, because due to the increased connectivity. And we need like a layered defense mechanisms to perform end-to-end cyber physical system security solution. Having said that, so let me stop here. So I think the slides will be made available after the talk, and my contact information also available in the slide. And I'd be happy to have any questions if we have. I see some two chat messages.
Yep, if you have any questions, please feel free to post your questions in the chat, and Dr. Hasan will answer those questions. I think there was one that already showed up if you want to go ahead and answer that question.
Yes, so let me try to open the chat. Okay, so I see. So the question was, from Corbett. So on the adversary, try to minimize the ACI time. So good question. So essentially the ACI time is given by the designer for a given system. So the adversary doesn't have any control when the system will run on during the ACI, or like the adversary doesn't have any control over that period, because only the all the control logic and applications will run during the in the untrusted controller. So if we can pull the slides. I'm sorry. So everything will be running during the, within the untrusted controller. So that the ACI time is kind of like fixed by the design time, and the adversary doesn't have any control, because the timer is set and reset by a separate root of trust, which is only available through the safety controller by design of the ReSecure framework. I have another question for Sengzi regarding TrustZone. As far as I know, you can run a normal hypervisor in the normal world, or use a secure EL2 to run secure hypervisor in the secure world. I'm not clear what's the TrustZone hypervisor in the slide across normal world and secure world. Is it a modified secure monitor or something else? Thanks. Yes, good question. So yes, so this hypervisor is it's based on the LTZ visor hypervisor, which is designed for this low power real-time / CPS application, so that allows to boot different type of virtual machines. So what you said is right. So we can have multiple hypervisor in different world, but this LTZ visor hypervisor that we used as our base, that allows to run as a hypervisor, kind of like you can think of like a monitor, like secure monitor in TrustZone. So that allow us to run two different types of virtual machines. So this is another type of TrustZone virtualization. I hope that answers your question. So if we have any more questions, so I'm happy to answer that.
Let's give it a couple seconds, Dr. Hasan, and see if anyone has any additional questions.
Here, I got another question from Roman. When discussing rebooting, how long about would it take for the system to reboot? It can be more than a few seconds at the most. How is this possible? Okay, excellent question. So in fact, we did a lot of experiments on analyzing the reboot time. And it also depends on the type of the hardware and the operating system that we use. So we find we can reboot in a very few, even order of seconds in some platforms. So I can't remember the name of the platform on top of my head, but it's some Freescale NXP platforms that allows us to reboot very fast time. It's even a less fraction of seconds. But we also saw for some platforms, for instance, especially those running like a Linux and more like advanced SoCs, they take quite a bit of time. Even that takes like more than like 2-3 seconds. So those, depending on the system dynamics and type of the operating system, it could be costly. So essentially, this is one of the reasons we are kind of moving from that ROT-based reboot through to the TrustZone-based techniques. Because depending on the system dynamics, if that is like a very fast system, for instance, like a drone or autonomous vehicle, we may, and we need to use like a more advanced software OS, that reboot time could itself be a bottleneck. So yeah, you're right. Any further questions? Okay, I have another question from Chip Corbett. How long would it take to reboot a modern automobile? Okay, so here's the thing. So when we say reboot a automobile, we may not refer to just freeze the whole vehicle and reboot everything, right? So it could be just one ECU we need to reboot, right? So and for those systems, there often remains multiple redundant entities, right? And even when we do the rebooting, the system is not like, it's not like that the system is not receiving any signals, because we remember we have the safety controller that is also still live in the system. So whenever we, for instance, if we need to send certain signal to certain actuators, or for instance the wheels, the safety controller could do that. So even if the system remain unavailable from the untrusted controller side, we could design a safety controller that always interact with probably the critical actuators of the system, so that it's not like completely frozen. But in the current work, we haven't explored in the automobiles use cases per se.
Okay, well, thank you so much, Dr. Hasan, for your presentation. Great information shared to the community. Let's take a 5-minute break. We will resume at 2 o'clock Eastern Standard Time with our second presenter. And thank you again, Dr. Hasan.
Thank you,